Alright, welcome back. This is going to be a supplement to part 2. I'm going to perform another factor and cluster analysis, except this time on a different data set. So here we actually have some coronavirus data taken from July 31st. Here we have the total number of cases, the total deaths, the death rate, and the population density for each state. So total cases is the total number of COVID-19 confirms. The total deaths is the deaths from coronavirus. The death rate is simply the total number of the total deaths divided by the total number of cases. So we can say Alabama has a 1.81% chance of death if you contract COVID-19. And then here we have the population. The population density is simply the population divided by the landmass. So there's on average 1.3 people per square mile in Alaska. And so we want to see with this data set if we can actually take out any kind of information. So the first thing we're going to do is actually import this into our matrix. Into our software. Oops. All right. So we have a 50 by 5 matrix. I'm going to take the mean. And so here we actually have the average number total of cases is 86,000. The average total deaths is almost 3,000, and the average death rate is about 3, and the population, average population, is about 65 million, and the average population density is about 200, so about 200 people per square mile. And so from this, we can now actually perform, we can see the correlation on our data. So we can see here that variable 1, total number of cases, has a somewhat of a direct correlation with the number of deaths, has no influence on death rate, and has an extremely high correlation with population. So we can say that as population increases, our total number of cases is going to increase as well. And it's interesting to note that total number of cases has no correlation with population density. So this almost seems counterintuitive. With places with more population density, we would expect higher cases, but from this analysis, we can almost say that there's no correlation. However, it is interesting to note that the death rate appears to be highly correlated with population density. So for variable 3, death rate is highly correlated with population density. So even though the total number of cases is not directly correlated with population density, the death rate is. So that's very interesting to note. We can even check out the covariance matrix. So we can see here we have some pretty sporadic numbers. There appears to be lots of variances between the total number of cases, total deaths. Death rate has a low variance. So, and the covariance values are extremely large. So this is pretty interesting to note out. And we can even check out just the z-scores, just as a preliminary. So now I'm going to perform a cluster analysis first on the variables. Oh man, I the wrong one, don't I? We will use the z-scores, perform on the variables. So we can see here that, let's take Ward's method first. The largest distance between two merged clusters appears to be this right here. So we would probably say two distinct clusters on the variables. Average linkage would probably be 2 as well. Complete linkage probably be 2 as well. Single linkage would probably be 3. So we can say our variables can be reduced down to 2 main clusters. And so that's going to aid us in our factor analysis. We will use the z-scores, scatter plot the data. And so here, variable 1 versus variable 2, there's not so much of a direct correlation, but there is somewhat. And we can see here the correlation is basically 0 for variable 1 versus variable 3, and we can definitely see this. There's no correlation at all whatsoever between the death rate and the total number of cases. However, variable 1 versus variable 4, the population and the number of cases is directly correlated. And the population density versus the total number of cases has no correlation whatsoever. We can see this, there's just sporadic. We can see this for the other ones as well. Examine outliers, yes. You know from the empirical rule that 99.75% of the data is going to lie within 3 standard deviations. So anything outside of 3 standard deviations would be considered an outlier. So here we have the chi-square quantile. We can see here that the largest outlier would be index 33. If we were to go here, we would have to account for it being 0 indexed and plus 1. Because of this, the labels would be actually line 35. So New York is the largest outlier. And we can sort of see why. Unfortunately, the mean is gone. That's not good. But the death rate for New York is 7.8%, which is one of the largest. You know, you can see Connecticut has a 9% death rate. New Jersey has an 8.7% death rate. The population density for New York seems to be above average, not necessarily large like Rhode Island or New Jersey. The population for New York is on the high end for sure, 19 million. The total number of cases for New York, 41,000, appears to be the largest except for Florida and California. But the number of deaths in New York is the highest by far. 32,000 deaths in New York. So even though that California and Florida have comparable number of cases for New York almost appears to double and even triple the number of deaths. Actually, not even triple, it's almost 5 times the number of deaths as Florida. That's very interesting. So that's probably why New York seems to be an outlier. I will not remove these outliers because these are actual observations and not simply mishaps in taking of measurements. We'll assess normality. And I'm going to pause and replay when these graphs appear. And so here these graphs have appeared. And we have these square distances. So we can say our data is approximately normal, except for we have our 3 outliers again. New York is extremely just far out. And these QQ plots for the univariate variables would be not necessarily important since we're taking account into all variables, but these would be good for just considering a univariate stance. So now we're going to perform principal component analysis. And so here we have the eigenvectors, we have our eigenvalues and a scree plot. We can see that there's not necessarily a distinct elbow. It seems to bend here at principal component 3, which explains these three components explain about 95% of the variability in the data. So we can reduce this 5 variable data set into probably 3. It's interesting to note that we even said 3 in our previous cluster analysis on the variables. So go back. Here we have the biplots again, so we can sort of see we have some outliers, not necessarily some distinct clusters in the data. You could maybe argue this could be a cluster and that could be one as well. And so it's going to exit out of all these. We will use 3 factors in our analysis. Let's rotate in the direction of x1. So we rotated through x1 through an angle of 415 degrees, or 46 degrees. And it seems that x1 has stayed the same, which is to be as expected, and loading 2 and loading 3 has changed. And we're going to keep it this way. We're going to not rotate through any more angles. So here we have our factor analysis report. We explain about 95% of the variability in the data. You know, pretty good, 97%, 94, 91. So we're missing some of the variance in variable 3, which is the death rate. So we're not explaining a lot of the variability in the death rate, but that's all right. We can say that factor 1 is highly correlated with these 3, extremely well correlated with these 3 variables. So if we were to go back, factor 1 is directly correlated with the total number of cases, the total deaths, and the population. Whereas factor 2 has sort of correlated with the death rate, not really whatsoever actually, but the population density is correlated with factor 2. So we have 2 main clusters here of variables. We can see factor 1 versus factor 3. Factor 3 explains a lot in terms of the death rate negatively. And factor 1, we already have that. So factor 2 versus factor 3. Factor 3 explains a lot of the variability in x1 and x4. Factor 2 explains a lot in x5. So now we can say that 3 factors would be a good observation. We will not export the factor loadings. And here we have the factor scores biplot. So we can say factor 1 has a lot of correlation with factors 2 and F3. And then here we have factor 1 versus factor 2. We could almost argue this would be a small cluster of some sort, or just simply just outliers. And so we can say here that we have 3 main underlying latent variables in our data set. We can seek to explain this probably by, we can say, as previously stated, our first underlying variable is highly correlated with x1, x2, and x4. So total number of cases, deaths, and population probably be one of the latent variables. F2 simply just explains a lot of the population density. So this would probably be our second underlying variable, and then F3 simply explains what appears to be a little bit of the total cases, most of the deaths, and a little bit of the population. So this would probably be a mixture of these 3 variables would be our third underlying variable.